Hello and welcome to our today's session. My name is Rüdiger Schickhaus. I'm working at Microsoft in the Global Black Belt team responsible for data and AI. In our today's session, we will focus on data loading best practices, loading techniques for a cloud-scale enterprise data warehouse in Azure Synapse Analytics. As a presenter, I encourage you to think about these scenarios, apply to your own or your customers' business problems, and how you see the potential of how you can help providing better insights through cloud-scale analytics. I appreciate and welcome questions during the presentation, but realize that not all your questions might be addressed, so I might defer you to the question and answer section of this presentation. In this session, we'll focus on how to optimize data loading at volume in a cloud-scale enterprise data warehouse, Synapse Analytics. Load petabytes of data into Azure Synapse Analytics data warehouse or database in minutes by using PolyBase. We will explore how PolyBase works, and we will drill down into the definition of PolyBase and learn how to apply data loading best practices. Azure Synapse Analytics supports many loading methods. These methods include non-PolyBase options such as BCP or the SQL bulk copy API. The fastest and most scalable way to load data is through PolyBase. PolyBase is a technology that accesses external data stored in Azure Blob Storage, Hadoop, or Azure Data Lake Store via the Transact SQL language. With PolyBase, you can import data from a variety of formats and sources to populate your data warehouse with all of the data you need to analyze. If you haven't heard about Azure Synapse Analytics, then let's start demystifying some of the areas around it. Azure Synapse is Azure SQL Data Warehouse evolved. Azure Synapse Analytics is a limitless analytics service with unmatched time to insight that delivers insights from all your data across the data warehouse and big data analytics systems with blazing speed. In this session, we will be focusing on the key Azure Synapse Analytics data warehouse features. With the big data feature, at the time of writing, you should call out that the relational big data capabilities is live today. The non-relational big data capabilities will be available in the future. Furthermore, data integration and a unified GUI will also be provided in the future for complete solution. With the volume and complexity of data rapidly increasing, performance and security are critical requirements for analytics. But not all analytics services are built equal, and not all cloud storage is built for analytics. Only Azure provides the most comprehensive set of analytics service, from data ingestion to storage to data warehousing to machine learning and BI. Each of these services have been finely tuned to provide industry-leading performance, security, and ease of use at unmatched value. In short, Azure has you covered. In the most recent study of GigaOM, they found that Azure SQL Data Warehouse is now outperforming the competition up to whopping 14 times. No one else has produced independent, industry-accepted benchmarks like these. In this session, we will be focusing on the key Azure Synapse Analytics Data Warehouse features. First of all, we have to talk about PaaS service, Platform as a Service. Azure Synapse is an analytical service that brings together enterprise data warehousing and big data analytics. It gives you freedom to query data on your terms using either serverless on-demand or provisioned resources at scale. Azure Synapse brings these two worlds together with a unified experience to ingest, prepare, manage, and serve data for immediate BI and machine learning needs. No installation is necessary, just select your service and start working. This industry-leading price performance extends to the rest of your analytics stack. This includes Azure Data Lake Store, our cloud data storage service, and Azure Databricks, our big data processing service. Azure Synapse delivers insights from all your data across the data warehouse and big data analytics system with blazing speed. With Azure Synapse, data professionals can query both relational and non-relational data at petabyte scale using their familiar SQL language. This can be done with big data, with SQL data, with relational data, and in the future also with non-relational data. Pausing and resuming is one of the features coming with the PaaS service. You can use the Azure portal or you can use Azure PowerShell to pause and resume the Synapse SQL pool or data warehouse. Compute resources. To reduce costs, you can pause and resume compute resources on demand. For example, you won't be using the database during the night and on weekends. You can pause it during those times and resume it during the day. You won't be charged for compute resources while the database is paused. However, you will continue to be charged for storage. Azure Data Lake Storage provides multi-layered security, including POSIX-compliant file and folder permissions, and at-rest encryption. Azure Data Lake Store Gen 2 is a highly scalable and cost-effective data lake solution for big data analytics. It combines the power of a high-performance file system with massive scale and economy to help you speed your time to insight. Data Lake Storage Gen 2 extends Azure Blob storage capabilities and is optimized for analytic workloads. Data Lake Store Gen 2 is the most comprehensive data lake available. Separate storage and compute gives you absolute flexibility which tool to use when with your data. And finally, the workload management. For mission-critical workloads, they can easily be optimize the performance of all queries with intelligent workload management, workload isolation, and limitless concurrency. For Azure Synapse Analytics, the price performance in the world means nothing without security. Make the comparison and you will see Azure as the most trusted cloud in the market. Azure has the most comprehensive set of compliance offerings, including more certification than any other cloud vendor, combined with advanced identity governance and access management with Active Directory integration. Azure Synapse is a limitless analytics service that brings together enterprise data warehouse and big data analytics. It gives you the freedom to create data on your terms, either using serverless on-demand or provisioned resources at scale. Azure Synapse brings these two worlds together with a unified experience to ingest, prepare, manage, and serve data for immediate BI and machine learning needs. Azure has the following component. SQL Analytics, which is a complete T-SQL-based analytics engine. It comes with SQL pools, pay per data warehouse unit provisioned. This is general available today. The data warehouse architecture in Azure Synapse Analytics is built around the core fundamentals of massively parallel processing, also called MPP. SQL Analytics uses a node-based architecture. Applications connect and issue T-SQL commands to a control node, which is the single point of entry for SQL Analytics. Synapse SQL leverage a scale-out architecture to distribute computational processing of data across multiple nodes. The unit of a scale is an abstraction of compute power that is known as data warehouse unit. A control node takes over ownership of query orchestration. The control node runs the MPP engine, which optimizes queries for parallel processing, and then passes operations to compute nodes to do their work in parallel. When a query is submitted to the data warehouse, the query is pushed down for processing to each of the compute nodes. Compute is separate from storage, which enables you to scale compute independently of the data of your system. The compute nodes store all your data in Azure Storage and runs the parallel queries. The Data Movement Service, also known as DMS, is a system-level internal service that moves data across the nodes as necessary to run a query in parallel and return accurate results. Compute nodes. The compute nodes provide the computational power. Distributions map to compute nodes for processing. As you pay for more compute resources, distributions are remapped to available compute nodes. The number of compute nodes range from 1 to 60 and is determined by the service level of Synapse SQL. Each compute node has a node ID that is visible in system views. You can see the compute node ID by looking for the node ID column in system views whose name begin with sys.pdw_nodes. For a list of these systems, you can also see the MPP system views. With decoupled storage and compute when using Synapse SQL Pool, one can independently size compute power irrespective to your storage needs, grow or shrink compute power within a SQL pool or data warehouse without moving data, pause compute capacity while leaving a data intact so you only pay for storage, resume compute capacity during operational hours. A typical data warehouse consists of provisioning the data warehouse, loading the data, and making data available for querying. The provisioning and load process can be accomplished through workflow automation in Azure Data Factory. In the next chapter, we will cover some loading design goals. Optimizing and speeding up data loads without impacting the performance of ongoing queries is on the design goals in data warehousing. Let's have a look on some details. Core concepts around loading data efficiently is doing so in a non-obtrusive manner. During data load, the core goal is to reduce fragmentation and provide a reinitiate status with system recovery capabilities as well as reduce overall query performance impact. When you know in advance your primary operations and queries to be run in your data warehouse, you can prioritize your data warehouse architecture for those operations. These queries and operations might include joining one or two fact tables with dimension tables, filtering the combined table and then appending the results into a data mart, making large or small updates into your fact sales, appending only data to your tables. Knowing the tables of operation in advance helps you optimize the design of your tables. Provide system recovery capabilities in the event of data loading failure with minimal impact on concurrent queries. First, load your data into Azure Data Lake Store or Azure Blob Storage. Next, use PolyBase to load your data into staging tables. Use some of the following configurations. The distribution should be initially round-robin. For indexing, you should use the heap indexing. Partitioning is in the first step not required. The resource class should be large RC or X large RC. Some tips. Always start with round-robin method, but aspire to a hash distribution strategy to take advantage of a massively parallel architecture. Make sure that common hash keys have the same data formats. Don't distribute on bar chart format. Dimension tables with a common hash key to a fact table with frequent joint operations can be hashed distributed. Loading of data could be accomplished using multiple load methods. In previous sessions, we discussed data ingestion, data storage, and an overall modern data warehouse architecture. Let's focus on how we will load data from cloud-based storage directly into a data warehouse in Azure Synapse Analytics. In a cloud solution, data is ingested into big data stores from a variety of sources. Once in a big data store, Hadoop, Spark, and machine learning algorithms prepare and train the data. When the data is ready for complex analysis, Synapse SQL Pool uses PolyBase to query the big data stores. PolyBase uses standard T-SQL queries to bring the data into Synapse SQL Pool tables. Synapse SQL Pool stores data in relational tables with columnar storage. This format significantly reduces the data storage costs and improves query performance. Once data is stored, you can run analytics at massive scale. Compared to traditional database systems, analysis queries finish in seconds instead of minutes, of hours instead of days. The analysis results can go to worldwide reporting databases or applications. Business analysts can then gain insights to make well-informed business decisions. In common data load scenarios, you might have previously used command line tools like BCP or a graphical tool like SQL Server Integration Services or SSIS. The bulk copy program utility, BCP, bulk copies data between an instance of Microsoft SQL Server and a data file in a user-specified format. The BCP utility can be used to import large numbers of new rows into SQL Server tables or to export data out of tables into data files. Except when used with the query out option, the utility requires no knowledge of Transact SQL. To import data into a table, you must either use the format file created for that table or understand the structure of the table and the types of data that are valid for its columns. If you use BCP to back up your data, create a format file to record the data format. BCP data files do not include any schema or format information, so if a table or view is dropped and you do not have a format file, you may be unable to import the data. Microsoft Integration Services is a platform for building enterprise-level data integration and data transformation solutions. Use integration services to solve complex business problems by copying or downloading files, loading data warehouses, cleansing and mining data, and managing SQL Server objects and data. Integration services can extract and transform data from a wide variety of sources such as XML data files, flat files, and relational data sources, and then load the data into one or more destinations. Integration services includes a rich set of built-in task and transformation, graphical tools for building packages, and the integration service catalog database, where you store, run, and manage packages. You can use the graphical integration services tool to create solutions without writing a single line of code. You can also program the extensive integration service object model to create packages programmatically and code custom tasks and other package objects. PolyBase is another technique which is extremely popular for parallel data loads and part of the best practice of loading data into enterprise data warehouse. We'll have a detailed look on how to use PolyBase and how PolyBase is a common data load scenario in cloud scale analytics. PolyBase is designed to leverage the MPP data warehouse architecture of Azure Synapse Analytics and will therefore load data faster than any other data tool. PolyBase integrates with Azure Data Factory, so you can use PolyBase to integrate in an ADF workflow to support a data pipeline. As PolyBase handles the load capabilities of a variety of file formats, it's a versatile instrument to optimize and accelerate data. Traditional SMP SQL pools use an extract, transform, and load ETL process for loading data. Synapse SQL Pool within Azure Synapse Analytics has a massively parallel processing architecture that takes advantage of the scalability and flexibility of compute and storage resources. Using an extract, load, and transform process leverages MPP and eliminates the resources needed for data transformation prior to loading. While SQL Pool supports many loading methods, including popular SQL Server options such as BCP and the SQL Bulk Copy API, the fastest and most scalable way to load data is through PolyBase, external tables, and the copy statement. With PolyBase and the copy statement, you can access external data stored in Azure Blob Storage or Azure Data Lake Store via the T-SQL language. For the most flexibility when loading, we recommend using the copy statement. By configuring PolyBase, you'll identify the external data source, file format, then create what are called external tables. You could configure this using T-SQL syntax. In this slide, it's explained the three core components in PolyBase. The one is external data source, the other one is external file format, and both can lead to external tables. External data sources command creates an external data source for PolyBase. External data sources are used to establish connectivity and support the following primary use cases: data virtualization and data loading using PolyBase. Some of the external file formats which are supported by PolyBase are the limited text, Hive RC files, Hive ORC, Parquet. To create an external table, use the command create external table from Transact SQL. External tables are used to query Hadoop or Azure Blob Storage data with Transact SQL statements. You also can use it to import and store data from Hadoop or Azure Blob Storage, import and store data from Azure Data Lake Store. Now that we learned about PolyBase for data loading, let's look into some of the details how to apply data loading best practices. PolyBase cannot load rows that have more than 1 million bytes of data. Split large compressed files into smaller compressed files for the fastest load and use compressed delimited text files. To minimize latency, co-locate your storage and layer and your SQL pool. When exporting data into an ORC file format, you might get Java out-of-memory errors when there are large text columns. To work around this limitation, export only a subset of the columns. PolyBase can't load rows that have more than 1 million bytes of data. When you put data into a text file in Azure Blob Storage or Azure Data Lake Store, they must have fewer than 1 million bytes of data. This byte limitation is true regardless of the table schema. All file formats have different performance characteristics. For the fastest load, use compressed delimited text files. The difference between UTF-8 and UTF-6 performance is minimal. Best practice is also to split larger files so they can allow for parallel processing in the compute nodes. In order to optimize load speeds, it's important to reduce the amount of concurrent processes. For fastest loading speed, run only one load job at a time. If that isn't feasible, run a minimal number of loads concurrently. If you expect a large amount of loading jobs, consider scaling up your SQL pool before the load. To run loads with appropriate compute resources, create loading users designated for running loads. Assign each loading user to a specific resource class and workload group. To run a load, sign in as one of the loading users and then run the load. The load runs with the user's resource class. In order to optimize for faster load speeds and assigning data loads to designated resource classes, it's recommended to create a dedicated load user account. Create loading users for running loads. Assign each loading user to a specific resource class. This method is simpler than trying to change a user's resource class to fit the current resource class need. There's often a need to have multiple users load data into a SQL pool. Loading with the create table as select transact SQL statement requires control permission for the database. The control permission gives control access to all schemas. You might not want all loading users to have control access on all schemas. To limit permissions, use the deny control statement. If you have thousands or more single inserts throughout the day, batch the inserts so you can bulk load them. Develop your processes to append the single inserts to a file, and then create another process that periodically loads the file. Let's have a look how our singleton inserts move through the control node, then to the allocated compute node. Singleton loads or small transaction loads create unnecessary flow of data. Goal is to group the append of a singleton insert to files and use a faster load option by batch importing. A common scenario in loading data is by using a two-step load process that involves the creation of staging tables. Usually, to achieve the fastest loading speed for moving data into a data warehouse table, load data into a staging table. Best practices would be to define the staging table as a heap, that's a non-indexed table, and use a round-robin mechanism for the distribution option. Define the staging table as a heap and use round-robin for the distribution option is the best practice here. However, if the production table uses a hash distribution, the total time to load and insert might be faster if you define the staging table with a hash distribution. Loading to the staging table takes longer, but the second step of inserting the rows in the production table does not incur data movement across the distributions. To improve query performance, it's important to create statistics on all columns of all tables after the first load, or substantial changes occur in the data. This can be done manually, or you can enable auto-create statistics. So welcome to our demo, how we load data into Azure Synapse Data Warehouse by using PolyBase. In the first exercise, what we are doing there is we connect with the Management Studio from SQL Server to our already created in the before exercise already created Azure Synapse Data Warehouse. What we have to do there first is we have to collect in the Azure portal our key, our storage account key. This can be done by simply going to your storage account and go to the key section there and collect your key number 1, copy that into the secret section. The identity is block identity, and before that, we have done that already in an earlier exercise, we had to create the master key. So if we would rerun that, as I have done here, it tells us the Azure Storage credentials are already existing, so we can skip that session for now. In the SQL Server Management Studio, in the query window now, we have to type in the code, and I have done that upfront to save some time here. We have to create an external file format named text file. I already tested this before, and this is why I named that now text file 2. We want to have a delimited file format. The field terminator is the comma. We simply mark this now and run the statement, and the command completed successfully. And what we then will find is that we will have an external file format, and after we refresh the GUI, we have the file format text file 2. In the SQL Server Management Studio, we go now to the next section, and what we want to do there is we will create an external table named dbo.dimdate2external, and the location as the root file and the data source should be our Azure Storage. The file format is the text file 2 format with which we created upfront. We will use those columns, a date key, month key, so basically we create a dimension for the data warehouse. The location should be dimdate2.txt. The data source is Azure Data Storage, and the file format is text file 2 as we have created here. So what we do now is we select the whole statement, we execute the statement, the command completes successfully, and now we can do the following. We can do a select on this external table. Copy that statement, and what we see is now we have data in here. We can double check if everything is filled correctly. Everything's fine for this. The next step in the SQL Server Management Studio is that we create a table named dbo.dates with a column store index and a distribution of round robin. That loads data from the DB2 external table into our DB2 dates, DBO dates table. We do this by using the create table with as select from statement. And once we execute that statement, it tells me the table already exists because I have run this before and the table is already there. So we don't need to rerun that. And if we go to the table section, we found the DBO dates. So what we can do, just to demonstrate how the SQL Server Management Studio works, we want to create a drop statement. This is done by right-clicking on the existing table. We get already the drop statement. We execute the drop statement. The command completes successfully. Once we refresh the window here, it takes some seconds, and then the table should be gone. We go back to our statement, rerun the statement, and this time the statement should work as we have dropped the table. The last step, what we have to do is we create the statistics on this just created table. Therefore, we execute the create statistics statement on the date key, on the quarter, and the month. And the final statement, just to make sure everything works correctly, is that we execute a select. And what we have done is we have created a dbo.dates table in the SQL Data Warehouse by using PolyBase from SQL Server Management Studio.
Welcome to Optimizing Data Warehousing Query Performance. Our agenda for today will be what is Azure Synapse Analytics and what is its architecture, how does it look like, what are the data loading best practices, and what are various techniques you can use for query optimizations. So let's get started. What is Azure Synapse Analytics? Azure Synapse Analytics is a limitless analytics service which delivers insights from all your data across data warehouses and big data analytics systems, and it has a really high performance. So you can use that as a single point of interactions with all your data, whatever it sits on the big data environments or in the warehouses. And it's what Azure SQL database data warehouse evolved from.
So what in fact is Azure Synapse Analytics? Azure Synapse Analytics is a newer service which combines the power of several main services like Azure Data Factory, Azure DW, and some others, and brings these kind of in one single experience and it tightens integration between those services. So basically, it's the way or the tool which allows you to build and use your data warehouses and all the other services around that, like analytics services, like Spark, like some ML services, as one native tool for data warehouse. So which eliminates in turn a lot of different integration and makes your life just simpler.
The process of working with data warehouse is pretty simple, and it consists of three major phases. The first phase is the provisioning, where we provision the data warehouse or the virtual clusters themselves, where we are putting or creating the data structures we are planning to use, like schemas, like stored procedures, like internal, external tables, views, and so on and so forth, right? And then on the second phase, we're loading the data into the data warehouse. We can use multiple different ways, and we talked today about that. We can use, for example, PolyBase, or we can use Azure Data Factory to load this data, or these are the two major approaches. And after the data is loaded and it's validated and this process is defined and executed, then we can start querying the data. And we're going to mainly focus on querying in this session. And the entire workload can be automated or can benefit from automating via Azure Data Factory as well. So how data warehouse architecture works? Data warehouse is an MPP system. That means that whenever the request is done against the data warehouse cluster, it's done against the control node, which creates the execution plan and distributes that across the compute nodes. Compute nodes process these execution plans, which are dedicated to them, then return the data to the control node, and the control node performs the necessary operations like the sorting, like the grouping on all the portions of data received from the compute node, and send the request back to the requester, to the application, or to the user.
So when we're talking about the query optimization and generally about optimization and using the Azure Synapse Analytics, we need to keep in mind that the core of the database is in fact an MPP system, right? That means that the data and the queries are distributed across one or more data nodes where the queries are actually executed. And then they're brought back to the coordinator node where they're combined, sorted, aggregated, and sent back to the requester. This brings us to the situation where we have almost limitless scalability, especially when the storage is decoupled, and we have a really high performance. But it also requires some discipline in designing data and in designing your queries. And we're going to talk about that in a bit.
So Some of the things which, when we're referring to Azure Synapse Analytics and the performance of Azure Synapse Analytics, query performance is mainly happens here, right? So basically, the Azure Synapse as a box or as a cluster of compute and storage is acting as a serving layer and serves applications and BI tools, data analytics tools, and so on and so forth. So it's on the consumption side, and it's mainly the read queries we're talking about. But let's talk about the maximizing the performance. To maximize the query performance in MPP systems, we have three major table distribution styles. It might be round-robin tables. Basically, these tables are distributed evenly across all the compute nodes. It might be the hash distributed tables. These tables are distributed based on some hash key, and that might be replicated tables which are copied across all the nodes.
Just once again to emphasize this part, the query performance or like the distribution is there for optimizing the query performance. So you can, using the various the data as close physically to each other as it's possible. So multiple queries on the same or similar dataset or datasets which are part of the same query will be executed in parallel on multiple nodes, which will speed up the process as well.
So let's dive a little bit deeper in the various distribution styles, right? So round-robin distribution is a default option for all the newly created tables. So if you're not specifying the style you want the distribution to happen, it will happen in the round-robin. So the round-robin tables, the data in the round-robin tables is evenly distributed across all the available compute nodes in a random manner. So it provides the most even distribution style which can be achieved automatically. Important thing about round-robin tables is that loading into round-robin tables is very fast and very efficient, because under the hood all the compute capacity of the cluster is used and all the nodes are equally performing the same operation of data loading. So queries on round-robin tables, though, read queries, may require some more data movement, as data can be reshuffled between the nodes to organize and compute and storage is acting as a serving layer and serves applications and BI tools, data analytics tools, and so on and so forth. So it's on the consumption side, and it's mainly the read queries we're talking about. But let's talk about the maximizing the performance. To maximize the query performance in MPP systems, we have three major table distribution styles. It might be round-robin tables. Basically, these tables are distributed evenly across all the compute nodes. It might be the hash distributed tables. These tables are distributed based on some hash key, and that might be replicated tables which are copied across all the nodes.
Just once again to emphasize this part, the query performance or like the distribution is there for optimizing the query performance. So you can, using the various types of distributions, you can basically put the data as close physically to each other as it's possible. So multiple queries on the same or similar dataset, or datasets which are part of the same query, will be executed in parallel on multiple nodes, which will speed up the process as well.
So let's dive a little bit deeper in the various distribution styles, right? So round-robin distribution is a default option for all the newly created tables. So if you're not specifying the style you want the distribution to happen, it will happen in the round-robin. So the round-robin tables, the data in the round-robin tables is evenly distributed across all the available compute nodes in a random manner. So it provides the most even distribution style which can be achieved automatically. Important thing about round-robin tables is that loading into round-robin tables is very fast and very efficient, because under the hood all the compute capacity of the cluster is used and all the nodes are equally performing the same operation of data loading. So queries on round-robin tables, though, read queries, may require some more data movement, as data can be reshuffled between the nodes to organize, and on the control node later on to organize the data for the query in the appropriate way. So typically the use case for round-robin tables, it's either where you don't know or cannot define the proper, or cannot define as of now, for example, the proper hash key, or for staging tables where you need to load the data very fast and then process that and send it to or write it to the different tables with a different distribution style. Another distribution style is a hash distribution. Hash distribution distributes rows based on the value of the specific column. And this column is used as a hash. We're implementing or using a hash function on top of this column to assign each row to one of the distributions. Just for your reference, we have currently in the Gen 2, we have 60 distributions. So that means that these hash distributed tables might be distributed across 60 distributions. So the hash distribution tables are designed to achieve higher performance for queries that run against large fact tables, especially when it comes to the star schema. But the downside of that is that sometimes choosing a good distribution column is really crucial from one side, and from the other side, it might be not always very straightforward. So typically, we recommend to start with hash distribution with the tables which are greater than 2 gigabytes in size, or which are frequently updated, or where the data is frequently deleted. The main thing is that the column we use for hash distribution should not be a volatile column, and also it should be, or it should allow us to distribute the data evenly, as even as is possible, apparently, across all the distributions in the cluster. Sometimes we use the hash distribution based on the most frequently used joins, but it needs to be verified using the monitoring and query optimization approaches. The replicated table is a full copy of the table which is placed on every single compute node. It is done to minimize the movement of data. So if you have some small dimensional table where you basically, which you use quite often in the joins, then it doesn't make sense to distribute that evenly or distribute by hash across all the nodes, because you might see that as every query querying every node within the cluster or every distribution to get and to bring back the entire dimensional table. So for these dimensional tables, typically you can use the replication on every node. We recommend to use that with the tables which are less than 2 gigabytes in size, and which are used very regularly in queries especially in queries with simple predicates. Also, you can convert the existing round-robin tables to replicated tables. Then you can use task statements, because task statements are much more efficient on the replicated tables. These replications should not be used on the dimensional tables, especially which are updated on a regular basis, because that will blow up the consumption of the storage and it will reduce the speed of your queries. One more important thing is that frequent update of statistics and creating the statistics after loading of data is very important for correct working of the query optimizer. So we strongly recommend to create statistics right after loading and maintain the statistics over the course of life of this cluster. Let's talk about the query performance tuning. One of the most important features and most valuable features we presented in the last few years was a query data store. Query data store overcomes the limits which we previously used to have on system views outputs. Right? Query store takes queries and finds and fixes queries with plan regression. Right? So you can see the queries which produce multiple plans. You have 7 days of retention. So if you see that basically the particular query produces all the time, all the course of 7 days, different execution plans, you can cope with that, or you can force to use a certain plan, right? And also, it provides you with full query text. So if you have multiple queries running, right, with multiple plans, you can definitely discover that over the course of 7 days. So that also enables A/B testing with your Azure Synapse Analytics. So you can, using this system views, you can try out different shapes of the queries, of different texts of the queries to identify which performs better, or to identify some of the aspects of using Synapse with your preferred BI tool, for example. And also, Query Data Store allows you to identify, improve, and tune ad hoc queries. Right? So, for instance, it provides you with some insights on the queries which are most likely cause the performance issues. So, how query data store is structured? It's structured in the similar way as dynamic management views. So you have the query view. And basically, query data store provides some additional views into DMVs, right? So you have the query view where you can actually see all the queries and all the executions of these queries, right? Then you can see the query text if you need that. It's stored in the sysquery query text. Then, if you need to dive deeper and to take a look, and whenever this query produces a different plans, then you can dive into that using the plan view. And then, from the plan view, you can actually take a look and start working with the runtime statistics, right? Collected over the certain runtime statistics intervals. So basically, that gives you kind of 360 degrees over all the queries you have and all the queries in your which are running in your DW. So for in order to use the query data store, a user needs to have the view database state permission. And please note that DMB are in UTC time zone, right? So it's always UTC time whenever it comes to queries. So just keep this in mind. So how the query execution with query data store happens on the DW in the MPP world. So queries are issued against the control node of Azure Synapse Analytics. The control node passes the query onto the engine that makes use of Query Optimizer and which will interact with ShellDB to get information about the data in the database, kind of like statistics, for instance, and other information to decide the most optimal route to retrieve data. Then the information is returned back to the engine in the form of the execution plan. So now we have the execution plan. And execution plan is executed across the database, all the compute nodes which exist in this cluster. And after the query is executed, the information about the execution of the query is published to the query data store. Then this query data store is flashed to the disk every 15 seconds, and you may have up to 10 gigabytes of the max storage size here. There is a retention period which is by default 7 days, which is not by default, which is 7 days for query data store, and you can have maximum 200 query execution plans per query in the query data store. Another cool feature which we use here is Azure Synapse Analytics recommendation, and how it works that Azure Synapse Analytics publishes the telemetry data. And basically telemetry data is used for the recommendation generation, and it's collected over the 24 hours. So what data is collected is the data skew and replicate tables. It collects the execution statistics, it collects StemDB statistics, it collects adaptive cache statistics. So basically it provides you with some nice view by the Azure Advisor recommendations, right? By the recommendation API is published into the Azure Advisor recommendations.
So one of the really cool features of Azure Synapse Analytics is the Synapse Analytics recommendation engine, which actually grabs a lot of information from system views, from logs, from various like backend systems, and combine these into very nice dashboards which are provided to you, so you can see, for instance, if you have the skew, if you have uneven distribution of data, right? So where you can see basically which queries are performing slow, or if statistics is outdated, and also you can have this understanding of whatever something is needed from your side, which is pretty cool because you don't need to go and grab data from the system views or from different internal logs and so on. So it's united in one really nice looking tool.
So you can have 360-degree on several things, like suboptimal table distribution. So whenever you have or you don't have the skew on the table. Then whenever you need to fix the data distribution. So for example, it might say that a certain table requires the redistribution based on hash, or requires to be replicated on all of the nodes in the cluster because it's often used in joins. Then it gives you information about the cache misses, and whenever you need to provision additional capacity here. Then it gives you the TabDB contention information as well if you need to scale or update user resource class. And also it gives you the information and recommendation on suboptimal plan selection, right? So whenever your certain queries produce multiple plans, or whenever these multiple plans are used not appropriately, or probably you need to update, in this case, the table statistics.
Once again, in terms of the query performance, there is a bunch of ways to discover if your Synapse Analytics cluster performs well, if your data is evenly distributed, right? If you have some data sitting on one node, so your distribution is wrong, or if you need to provision additional cache capacity, for instance, or reduce the contention of the 10 dB, for instance. Also, you can use pretty much the same tools as you have in typical database, or in typical SQL database, like DMV views, like explain plans, and these will also show you not only what is happening, but what will supposed to happen if you're going to run the certain query, right? And basically, you can use also the typical and normal tools for DBAs and for developers to improve your queries. But also, we have the really nice looking tools for you to work on.
Apart from the direct tools which I use to improve, to monitor and to improve and to recommend you several, let's say, how to improve your queries and your way of working with DW, with Synapse, including the data distribution, there are several things which I would like to highlight in addition to that. So first of all, in Synapse, we do have some multiple different ways to optimize the data performance further, right? So apart from the table distribution, it's table partitioning, for instance, materialized views indexes, including the column store indexes, and result set caching. Also, we are using some interesting functions and approaches to optimize the query performance using the windowing aggregates, using the approximate execution like hyperlock lock, and some other things like group by rollup and so on and so forth. Let's talk about that. So yeah, we can see here the partitioning on the distribution, right? So what can happen, or how more you can optimize your data using the distribution, is that you have the logical table structure on the left, right? And then you're saying, okay, what I'm doing is I'm distributing by the, it's a hash distribution by order ID. And what I need to do, and this is distributed across multiple nodes in the cluster, or multiple distributions by order ID, right? And there is a range. In addition to that, and so for instance, it's pretty logical that I'm looking for a certain state for the certain order, but it's pretty logical also that I'm doing that within a certain date. So in addition to the distribution, I can use partitioning to say, okay, I want to partition that by date, right? So that means that the scan itself or the lookup will take less time on each particular node or each particular distribution to retrieve this data. Important thing is that in this situation, each shard is partitioned with the same date partition, right? So we're partitioning by date here, and basically you cannot have here like this 2nd of November and 3rd of November, and on the other chart it will be 1st and 3rd. It's not possible, right? All the shards will be allocated across all the nodes. And the second thing is that this technique only applies to the very large tables. So a minimum of 1 million rows per distribution and partition is needed for optimal compression and performance. So we need this partition to have at least 1 million rows in it, right? So that applies for large tables. Another thing we discussed is the windowing functions. We can have some really cool things, and we can do some really cool things and speed up our queries using the aggregate functions, for instance, like approximate count distinct, right? This function will, for instance, return to you the approximate count with a 2% or 98% effectively of precision, right? So the error rate is 2% for that. Also, we have some ranking functions and some analytical functions like lag, for instance, which returns to not only the for example, not only the value, but also the difference to the next value, right? Or there are like let's say the lead. So it will not only return the exact value, but the next value as well, right? And also we do some rows and range functions as well, which are very fast in terms of the performance and which are highly optimized. Also, we mentioned things like approximate execution. So we can see here an example between the execution of approximate count distinct and count distinct, right? So here we see on the top that approximate count distinct returns to us 540 as a result, and count distinct returns 542. So there might be the error rate, right? This error rate, the standard error rate, cannot be higher than 2% though. But on the right hand side, we see that what happens in the count versus approximate count distinct is that count actually spends way more time on the sorting or doing the distinct sort rather than the approximate count distinct, which uses mainly the index scan, right? So the performance of approximate count distinct is way higher than the typical count. As an example, right? We have some other approximate execution functions as well. Another optimization we do have, or another functionality we do support for query optimization, is the indexing. And we have three major types of indexes. One is a clustered column store index, which is basically where the data is stored in compressed column store segments. So basically we slice the data into the groups of rows. So you can perceive that as a micro partitions, and which are used to be stored and compressed together. So it basically allows us to achieve one of the best compression rates between the products of this segment, between the different DWs, I mean. And all the other rows are stored in the delta row store until the number of rows is large enough to be compressed in the column store. So we're using a combination of optimization techniques to allow or to achieve the best performance and best compression here. Another type of indexes we can use is a clustered or non-clustered row store index. And basically, this is a classical B-tree index structure, and it's typically used for the lookup of the particular rows, while as column store index is just used for the wider and larger scans. And the row store index is just used for the lookups. And clustered row store index is basically when the data is stored physically in the leaves of the B-tree index, while as the non-clustered or secondary row store index is where the leaves are storing just the pointers to the data values, not the data values themselves. So the clustered row store index in this sense will perform better, but the good thing about non-clustered column store indexes, row store indexes, is that you can use as much of them as you want. Another thing is that we can do the ordering on the clustered column store index. So that means that this data will not only be stored in the column segments and then sliced into row groups and then column segments, and then stored in the column store index, which will be very efficient in terms of the compression, but also it can be ordered within this column store index. So it will drastically reduce the time needed to service a query, because first of all, the column store index just retrieves as the information very fast since it's compressed. The second thing is that because the data is already pre-ordered there, so we're eliminating one of the most expensive operations here. Another good piece of functionality we support in Synapse is materialized views. So we do pre-compute and store and maintain the certain portion of data in like a table way. So we update these materialized views automatically when the underlying tables are changed. So it's a synchronous operation, and that occurs very fast. Also, we do the auto caching, which allows Synapse Query Optimizer to consider using indexed views even if the view is not referenced in the query, right? So basically, our Query Optimizer can decide to use the materialized view instead of perform the real query if this materialized view is better in terms of execution statistics, right? We do support some of the aggregations for materialized views, like maximum, minimum, average, and so on, as a part of materialized view, right? So the benefit of using materialized view is that it's automatically and synchronously refreshes the data with the changes in base tables, and you don't need to perform any actions. And the high availability and resiliency is supported on the same level as the regular tables, although not all aggregations and not all operations are supported on materialized views. Another thing which is very important is the result set caching. So basically, the result set cache persists even if Azure Synapse Analytics is paused and resumed later, which is very important. And query cache is invalidated and refreshed when underlying table data or query is changed, right? So if the underlying table data like actually drastically changes, we're invalidating the cache, the query cache, and basically refresh that when the results coming back. And the result cache is evicted regularly based on the time-aware recently used algorithm. So we use the least recently used data to evict the data from the cache. Results of caching enhances performance and to the very high degree. It can be set up in the database on the database level or on the client session level, and basically it reduces the load on server, especially when you have the certain queries which are kind of repeatedly used. And also it offers monitoring of query execution with result cache hit and miss. It's actually part of the recommendation engine, so it's a pretty cool and important feature to use as well. One last point here is that we still support the typical DMVs, so which can give you some ideas around the table, basically around the server health, around server operations, and about like model objects, right? So apart from extended functionality and recommendations engine, you can use the typical SQL DMVs as well. So in summary, query performance, there are several main best practices when it comes to the query performance. So first of all, and one of the most important ones is to select the proper table distribution. But I would add here that you need to select and maintain a proper table distribution. So all of the time, look for the recommendations and check that out if the table needs to be redistributed. The other thing is to detect data skew. First of all, you can use query data store for that. And if you detect the data skew, especially when it comes, and you see that this data skew actually affects the performance of your queries, then consider changing key columns. And remember that the entire cluster is only as fast as the slowest distribution. Right? Other thing which can help quite often is to take a look at the adaptive cache and adaptive cache hit and miss metrics and provision additional adaptive cache capacity, and reduce MDB contention, and of course create and update statistics frequently. These are the main aspects of the query performance optimization. But also I would say that you might consider to use some faster functions we have, or some analytical functions in order to optimize your existing queries, and also use A/B testing with a monitoring results from query data store to optimize the performance.
So with that, we are closing today's session and today's event. Hope you enjoyed that. Hope you enjoyed the content, and thank you for being with us. This event is extremely important, especially in our current situation when we cannot deliver that face-to-face. So also thank you for asking all the questions in the chat. And if you have something extra, some extra questions, please feel free to put that right now in the chat. We're going to answer those, and we're going to distribute the answers to all the participants. We're going to be happy to see you in the following events or next events on different topics. So see you then, and thank you so much. Have a good day. Stay safe. Bye-bye.